Now let's practice solving some general right triangles. So we don't necessarily know that these are right triangles, and most likely they're not. So that means that the Pythagorean theorem isn't going to apply. So we're going to need the law of sines and the law of cosines instead. These first two examples are going to be a little bit derived because they're ones that we can solve nicely by hand. Most of these, once you start trying to solve them by hand, you get some really ugly answers, and so it takes a lot of work to rewrite it all, and it turns out just looking very, very ugly. If you have a calculator, it's not hard to plug them into your calculator and get all the pieces you need, but these two examples should give you the idea of how you would go about solving an entire triangle, and then we'll practice on different pieces, just doing one step on each. Okay, start with this example. So first of all, let's kind of take stock of what we have. I notice that I have this side and this angle. So I have one complete pair where we have a side and an angle opposite. I have one pair that's completely missing. And then I have one pair where I have a side and I'm looking for an angle. So because I have that pair, that complete pair, I think what I probably want to start with is the law of sines. So I'll set it up. The sine of 30 degrees over the side opposite, which is 4, is equal to sine of something over some other side. So this is the other side I know. So we'll put that in. And then the angle opposite is b. So we're taking the sine of b. So let's solve for b. First of all, I want to get sine b by itself, so I'll multiply by 4 root 3 on both sides. And then I can do a little bit of simplifying now, because those 4's are actually going to cancel. And I know the sine of 30 degrees. 30 degrees is one of my special angles, so if I write out my chart or if I have it memorized, I know that the sine of 30 is 1/2. So I get the square root of 3 times 1/2, which I can rewrite as root 3 over 2 is equal to the sine of b. So that means that b is equal to the sine inverse of the square root of 3 over 2. So we're thinking of, we're looking for the angle that has sine value square root of 3 over 2. That looks like one of the forms that'd be in my chart. So let's just start filling out the chart for sine, see how far we have to go. So we have 0, 30, 45, 60, 90. So they're all over 2. So sine of 0 is 0, so I have the square root of 0, so then I count up the square root of 1 over 2, the square root of 2 over 2, the square root of 3 over 2. So at 60 degrees, we're going to reach that the sine value has this value we're looking for. So B is actually a 60-degree angle. So now I have two angles in my triangle. So it shouldn't be hard to find angle A, because A plus 60 plus 30 should be equal to 180. So I get that A plus 90 is equal to 180. So when I move the 90 over, I'm going to actually end up getting that A is indeed 90. So obviously my drawing isn't to scale. And this actually is a right triangle. A sneaky right triangle. We needed to use the law of sines to find out more information, but it is a right triangle. So theoretically now we could go through and use the Pythagorean theorem. We know that A would be our hypotenuse and these two would be our legs of our right triangle. But just for the practice of it, and because we wouldn't be able to do that if A hadn't come out to be 90, let's set up the law of cosines to find our last piece. So we would set up A squared is equal to 4 squared plus 4 times the square root of 3 squared minus 2 times 4 times 4 root 3 cosine of big A, which we just found was 90 degrees. notice that the cosine of 90 degrees is actually 0. So this whole term is all going to disappear, and we end up with exactly the Pythagorean theorem. We said A was the hypotenuse, so we're taking the hypotenuse squared, and it's equal to the sum of the squares of the other two sides. So we get this, 16 times 3 is actually 48. We can either do that on paper or in our heads. So we get that a squared is equal to 64, which would tell me that a is equal to 8. So there we go, we've solved the entire triangle. It was a sneaky right triangle, but we were able to solve it using just the law of sines and the law of cosines and my angle sum in a triangle. Okay, now let's look at this example. This is another one that's going to be fairly easy to work by hand. So I have all three sides, but I don't have any of my angles. So I don't have any pair of a side and its opposite angle, since I don't have any angles. So I think I'm going to need the law of cosines here. I'm going to end up having to solve for the angle in the law of cosines. So I can start with any side. I want to start with this particular side. So I'm going to set it up. 4 squared is equal to 4 squared plus 4 square roots of 2 squared minus 2 times 4 times 4 root 2 times the cosine of the angle opposite the side where we started, which was A. So 16 equals 16 plus 16 times 2 minus 2 times 4 times 4 will give us 32 times the square root of 2 times cosine of A. Now, notice that I could combine these and then subtract the whole thing, but I noticed that 16, when I subtract it from both sides, is going to disappear. Then I need to subtract the 32 from both sides. So the 16s will cancel when I subtract it from both sides, and I subtract the 32 to get this. So I want cosine A by itself so I can solve for A. So I want to divide by this whole piece out in front. So those will cancel, the negatives will cancel. So what I'm left with is that cosine of big A is equal to 1 over the square root of 2. Now, if we want to be able to figure out which angle this is, what A is based on our chart, everything in our chart has this form. It's something square root over 2. This doesn't have that form, but I can actually make it have that form if I multiply by the square root of 2 over the square root of 2, which is what's called rationalizing the expression. I'm going to get the square root of 2 on top. I'm going to get 2 on the bottom when I multiply that. So I have something in this form. And if you go back to your chart, we see that the angle with cosine square root of 2 over 2 is actually 45 degrees, or pi over 4. So that's our answer for A, 45 degrees. So now I'm going to have to repeat this process. I'm done with this side. So I want to move over to this side. But before I go through and rewrite it all again, let's just think for a second. When I do write out the law of cosines for this, I'm going to get 4 squared is equal to this 4 squared plus 4 root 2 all squared minus 2 times 4 root 2 times cosine not of A, since we've already found A, but of C. In this particular triangle, it happens to be that when I set up the law of cosines for these two sides, all that changes is the angle. So all I need to do here is replace all my A's with C's and I'm actually already done with all the work, conveniently enough. So this angle is also 45 degrees. Again, this is a very specific type of triangle. If we had gone through and set it up and this had been different, we obviously would have had to go through and do it all again. It was just because the setup was all the same except for the angle name that we were able to reuse all our work. So now it shouldn't be hard for us to find B since we can just add up all these angles. And they should add up to 180 degrees. Well, these two add up to 90. So when I move the 90 to the other side, you can see that I've given us another sneaky right triangle. And that's just because these seem to be the easiest ones, or tend to be the easiest ones, to actually solve by hand using the law of cosines and the law of sines. But notice that we didn't know that until this very last step. I had no idea that this was a right triangle. So I had to go through all these steps in order to make sure that I knew for a fact I was working with a right triangle. Okay, so as I said, these were two derived examples. You see that they were both sneaky right triangles. And most triangles will follow the same steps, but the answers for these things will come out much less neat. Which is why for the rest of the examples we'll just do one step and then I'll kind of talk you through how we would finish them. So let's look at this triangle. So this side is 3, this side is 5, this angle is 51 degrees, and I want to find this other angle, this B. So, again, take stock. What do we have? I have an angle, I have the side opposite it. What I'm looking for is an angle, and I know the side opposite from it. So it looks like this is a fairly straightforward law of sines application. Because I can take the sine of 51 degrees, then put it over the side opposite. That's going to be equal to the sine of B over the side opposite. So this is very much like that first example we did. We can multiply both sides by 3. And then I can take the sine inverse. So B is equal to the sine inverse of all of this. And we don't know the sine of 51 degrees. It's not one of our special angles. So we can just leave it like this. Again, if you had a calculator, you could plug it in. Make sure that you're working in all degrees or all radians. This is in the domain of sine inverse because this is going to be between -1 and 1, and I'm multiplying it by 3/5. So that's still going to be between -1 and 1. So here's our value of B. This is just a number. If you were to plug it into your calculator, it would give you a number, and we're just going to treat that as our answer. Now, if we were to try and solve the rest of this triangle, I now have two angles. I could find the third by subtracting the rest from 180. Then I could find this last side by setting up the law of cosines. But you can see how ugly it would get to try and do that with this as one of our values. So, we're going to stop here, but you understand the rest of the steps, hopefully. Okay, let's start another example. Again, these triangles may or may not be to scale, most likely not. So I have two sides, one is 6, one is 11, and I know the angle in between them is 14 degrees, and I want to find the angle, or the side opposite that. So notice, I have 6, I don't have the angle opposite. I have 11, again, I don't have the angle opposite. I want to find this side, I have the angle opposite that. So this looks like a case for the law of cosines. So if I set it up, b squared is equal to 6 squared plus 11 squared minus 2 times 6 times 11 times cosine of the angle opposite the side we're working with, so 14 degrees. So 14 is not one of our special angles, so just like sine of 51 degrees, cosine of 14 degrees is probably going to show up in our answer somewhere. So let's see what we have here. We have b squared is equal to 36 plus 121 minus 2 times 6 times 11, so that's 66 times 2, it's going to be 132. I can combine these two, that's going to be 157. This is all equal to b squared, so I need to take the square root to find out what b is. So b is the square root of 157 minus 132 times cosine of 14 degrees. And that's as far as we'd go. We'd leave our answer there unless we had a calculator available to us. And you can see why we wouldn't then want to have to plug this back into the law of cosines to find one of these angles. If we wanted to, we could set up the law of cosines with this being the side we're solving for, solve for this angle. This could be the side that it's equal to, we'd solve for that angle. So that would be how we would finish out this triangle. Again, another triangle. This one we have all three sides and we want to find the angle in between two of them. So, in theory for this triangle, I could actually find any of those angles. It just depends how I set up the law of cosines. We're not going to do it all out 3 times. So let's set it up for this angle and then we'll talk through how we'd set it up for the other ones. So here, it's the angle opposite the 7 side, so 7 squared is equal to 4 squared plus 5 squared minus 2 times 4 times 5 times the cosine of that angle opposite the 7. So that's where the A comes in. If we, for instance, called this angle B and we wanted to find B, we would just set it up so we'd have 5 squared is equal to 4 squared plus 7 squared minus 2 times 4 times 7 cosine B. So all we have to do is just shuffle around where the sides go. If we called this angle C and wanted to find this angle, we would set it up so 4 squared is equal to 7 squared plus 5 squared minus 2 times 7 times 5 times the cosine of C. So we could find any of the angles here using the law of cosines. So that could be extra practice. If you want more practice with this, go through and find the rest of those angles. But we're just going to go through one. You'll see the process. It'll all be the same, just with different numbers. So we get 49 is equal to 16 plus 25 minus 2 times 4 times 5, which is 40, cosine of A. I'm going to combine these two. So I'm going to get 41 minus 40 times cosine of A. Move this to the other side. So we get 8 is equal to negative 40 cosine of A. Then I'm going to divide by negative 40. So cosine of A is equal to 8 over negative 40. But we can simplify that. We see that 4 goes into both of those. So we get 2 over, actually, we see that 2 goes into both, 4 goes into both, 8 even goes into both. We get 1 over 5, and that's still negative. So for A, we're going to get that A is cosine inverse of negative 1/5. And negative 1/5 is between negative 1 and positive 1. It's in our domain for cosine inverse. So that is our A value. Again, we just switch around where the numbers are, we'll end up with get both of the other two angles. Let's try one last example. So we know that this side is 7, this side is C, this angle is 42 degrees, and this angle is 70 degrees. So, let's take stock. What do we have? We have an angle, we have the side opposite, so thinking law of sines right off the bat. Then I have an angle, and I don't have the side opposite it, nor am I really looking for the side opposite it. What I'm looking for is opposite my blank angle. But if I call this angle C, big C, is it hard to find big C first before I use the law of sines? No, it's not. I have two angles, it's not hard to find my third. So 42 degrees plus 70 degrees plus big C should be equal to 180 degrees. So if I move the 70 over to the other side, I'll get 110 degrees over there. If I move the 42 degrees over, then I should get that C is equal to 68 degrees. So we had to insert an extra step here. We had one thing we had to do before we could use the law of sines. But now notice I have one complete pair, one pair where I know the angle, I'm looking for the side. So let's set up the law of sines. So sine of 70 over 7 is equal to sine of big C, which we just found, over little c. Now in order to solve for little c, let's cross multiply. So we get c times sine of 70, which we don't know, we can leave it like that, is equal to 7 times sine of 68 degrees. So all I need to do to get c by itself is divide by sine 70 on both sides. So I get 7 sine of 68 degrees divided by sine of 70 degrees. Then, in order to find the rest of the triangle, I could set up a second application of the law of sines to find my last side.